All right, this is a video for geometry on similar polygons, and we'll start off with a reminder, a couple introductions, and then we'll solve a few examples. So as a reminder, I want to talk about solving proportions, and I have other videos that go into this in more detail, but just quickly, we want to cross multiply here is the most efficient way of doing this. 9 times 4 is 36, 5 times x is 5x, and then we can divide both sides by 5, and we get 7.2 equals x. So just a quick reminder about cross multiplying to solve these proportions. And then another quick reminder about the quadratic formula. This will come up in some cases when we're solving for missing pieces of similar polygons. If we have this quadratic equation, ax squared plus bx plus c is equal to 0, reminder it has to be equal to 0, then this is the quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And a quick reminder that the plus or the minus will give us two possible answers, often, not always, but often. So let's do this quick example here. If x squared plus 2x is equal to 15, we need to force this equation equal to 0. We'll subtract 15 from both sides. And then we can write out what a, b, and c are. And as I'm doing this, I'll just remind you that there are quicker ways usually of solving quadratic equations. Factoring comes to mind here, but since this is a reminder of the quad formula, I'll take you through that process. A is 1, b is 2, c is negative 15. So let's plug our numbers in. Negative 2 plus or minus square root of 2 squared, which is 4, minus 4 times a times c, all over 2a, which is just 2. Students often run into a lot of problems trying to do too much simplifying inside the square root in your head. So my strategy is to write down all those numbers and simplify a little bit at a time, and just not try to overdo it. 4 minus 4 times 1 times negative 15 is negative 60. So that's going to turn into 4 plus a positive 60. And that's going to be a perfect square, I can tell. So that's nice and friendly. So x equals negative 2 plus or minus, the square root of 64 is 8 all over 2. When I get down to this point, I draw two pathways, and I do negative 2 plus 8, which is 6 over 2. And negative 2 minus 8, which is negative 10 over 2. And then simplify those to get a 3 and a negative 5. So that's our solution set. X is equal to a negative 5 or a 3. Okay, so quick reminder of the quadratic formula. But let's get back into what the main goal of this video is working with similar polygons. Okay, so for two polygons to be similar, which informally simply means they have the same shape, but not necessarily the same size, there are two criteria that have to be true. All corresponding angles have to be congruent, and all corresponding sides have to be proportional. Okay, so that's basically our definition of similar polygons, our mathematical definition of similar polygons. All corresponding angles have to be congruent, and all corresponding sides have to be proportional. So for this quick example here, you can see that these angles are congruent to each other. And when we talk about corresponding angles, we talk about really the matching angles in each shape. Okay, and then we can also see that corresponding sides are proportional. So if this side's a and this side's 3a, that's a scale factor of times 3. And that has to be true for all pairs of sides. Okay, so it's the same scale factor all the way around of times 3. Okay, so that's an example of two similar hexagons right there. So let's talk about similar triangles for a moment. And if I haven't mentioned it before, this tilde means similar to, okay? In contrast to the tilde above an equal sign means congruent to. Okay, so just a single tilde means similar to. So here we are being told that triangle MNP is similar to triangle SRT. Now, the order in which this similarity statement is written matters. This really means that M corresponds to angle S, angle N corresponds to angle R, and P corresponds to T. Okay, so we can do a little labeling here and say that angle M is congruent to angle S, and so that would be these two angles right here. We can say that angle N is congruent to angle R, so these two angles right here. And lastly, we can say that angle P is congruent to T. So I think it's a little bit confusing when we're working with similar triangles if the triangles aren't drawn in the same orientation. So if you can, I suggest redrawing the triangle, or maybe turning your paper, rotating your paper, doing what you need to do to get the triangles kind of facing the same way. And I'll do an example of that in a little bit. Write an extended proportion of the sides. So this means that we can say the side MN divided by its corresponding side SR. And I'm getting this by looking at this similarity statement up there. That's the corresponding side. MN over SR is going to be congruent to NP divided by RT, which then is going to be congruent to, let me show you how I'm doing this, MP divided by ST. Okay, so we just need to make sure that we're relating corresponding sides. MN here corresponds to SR here. And we also need to know that we're doing this consistently in a smaller divided by larger order in our proportion. It could be larger divided by smaller, that's fine, but you just have to be consistent all the way through. Okay, so that would be a correct extended proportion of the sides. Let's look at these here real quick. This question is, are they similar? Okay, so we'll look at this first one, and it looks like we have some corresponding angles that are congruent, so that's great news. Okay, so we have the angles all checked off. Corresponding angles are all congruent. Let's make sure corresponding sides are proportional. So 12 to 6, that's a factor of 2. But that doesn't apply over here. 6 to 6 is not a factor of 2, right? So here, this one would be not similar. And we just, as soon as we find one of the criteria that doesn't work, we can say the triangles are not similar. Okay, so it was really those two circled 6s that kept them from being similar. Let's look at this one. This one's a little bit more confusing because it seemed to be drawn where they're not facing the same way. So I am actually going to try to fix that here, and I'm going to see if I can face them the same way here. And I'm going to try to crop a little bit here. Let's see if I can make this work. Okay, and I'll try crop this one over here as well. Oops. Okay, so it looks like we have them somewhat facing the same way right now. Okay, we have, let's see, we have angle congruent to an angle, so those double arcs. Angle C is congruent to angle F, and angle B and E are congruent. So the angles are all congruent, again, so that checks off, so that's good news. Let's check the sides. So we want to make sure that 12 over 15, is that congruent to 16 over 20, and is that congruent to 8 over 10? Okay, so that's an extended proportion. I just matched up the congruent sides. If you can't do these in your head, I would just go to a calculator and check the decimals, and all of those proportions are equal, so that means they are similar. So then we can say here that triangle ABC is similar to triangle DEF. Okay, so they are similar. There's a scale factor of 0.8. The smaller triangle is 0.8 of the larger triangle in terms of side lengths. And there's our similarity statement. In this next one, we are being told that the shapes are similar, so we don't need to check to see if they're similar. We're being told they're similar. And so what we need to do is find the missing sides. And it looks like we need to find y and we need to find x. So first thing to do is to find the scale factor. And I'm going to work with this side over here. It looks to me like we can determine that this missing piece is a 3, right? 6 plus 3 has to equal 9. And so now we can determine that the long side, the longer of the two corresponding sides is 9, compared to the shorter of the two corresponding sides is 6. So that's going to help us set up our scale factor here. So let's go ahead and do that, and we can, let's set this up as long over short. So we have 9 over 6 equals, and now we can relate the 5 and the y. The 5 is the longer one, the y is the shorter one. And we can also relate the 7.5 and the x. So 7.5 over x. So let's first find y. So we can say 9 over 6 is 5 over y. Cross multiply and solve for y. So we have 9y equals 30. So y is equal to 3.3 repeating. Okay. And as a quick rough check, y needs to be smaller than 5, and it is. So that's a good way to check that. Okay, in part second one, let's solve for x. We can say, again, 9 over 6 is 7.5 over x. Cross multiply. We get 45 equals 9x, so x is going to equal 5. Okay, so we solve for the two missing sides of that quadrilateral. All right, we'll wrap this up with a little bit more of a real-world problem, a poster problem. And so the scenario here is that we have a design for a poster, and the design is 6 inches high by 10 inches wide. And so you might want to, I sometimes need to make a sketch, so it's 6 inches high by 10 inches wide, so wider than it is tall. And our space available is 4 feet high by 8 feet wide, okay? And so we want to determine the largest poster that will fit, okay? And I think what's implied here is we want to scale up this design by an equal scale factor in both the vertical and the horizontal dimensions so that our design doesn't look kind of skewed in one direction or stretched in one direction. What I'm going to do first is work with units, okay? So let's change our space available to 48 inches, and 8 times 12 is 96 inches wide. Okay, just to make sure we have consistent units. So if we just worked with the height and scaled things up just by the height, we could scale it up 8 times, okay? So we could do times 8. If we just worked with the width, we could scale it up. 96 divided by 10 is times 9.6. I hope you can see that if we scaled up our design by 9.6 times for both the height and the width, the height would be larger than the space available, okay? So we're gonna need to work with a scale factor of 8, okay? So let's have our new poster. Have a scale factor of 8. So 6 times 8 inches high by 10 times 8 inches wide. So that's going to be 48 inches by 80 inches. Okay, so that would be the largest poster we could fit in that space. Got through it, and that is a great place to stop right there.